So hi, Jeannette. Thanks for the interview today. So today we just wanted to talk a little bit more about a slightly different topic. Here at Ingrid Cloud, we're usually discussing, external fluid flow simulations. But today, our CFD engineer, Jeannette, she has some really interesting research relating to the medical field. So there are many interesting aspects about combining medical imaging with computational fluid dynamics. During your PhD research, you looked into simulation of blood flow passing through a heart valve, specifically the fluid structure interaction aspects. Is that correct?
Yes, exactly.
And what can you go into a little bit more about your research? What were the main challenges?
Yes. Yes. So, like the heart consists of 4 chambers, and whereas my research focused on the left ventricle. So the left ventricle is pumping the oxygenated blood from the lungs through the aorta back to the body. So it works a lot, it needs a lot of effort, and therefore this chamber is prone to heart disease. And the left ventricle possesses 2 valves, and we focused on the aortic valve. This is the one between the left ventricle and the aorta. And its functionality is that it ensures unidirectional blood flow, so that blood is flowing from the left ventricle to the aorta, and also prevents blood flow of flowing back. And so it has a function that which is opening and closing. So the valve itself consists of 3 leaflets. These are opening and closing based on the heart cycle. And the opening and closing is also controlled by the pressure difference between the left ventricle and the aorta. So you have this movement, right? This movement of opening and closing. And in order to model this, you have 2 challenges. The one is the fluid structure interaction, which is also called FSI. And you just mentioned in your introduction. So you have FSI is interaction, tries to model the interaction of the fluid. In this case, it is the blood, and the solid, which is the leaflets. So how the leaflets and the blood is interacting with each other, this was one challenge. And the other challenge is, so you have the interaction, but you also have contact, because you have to ensure that blood is not flowing back. So you have 2 complex problems which you have to solve in order to model the movement of the leaflets. So fluid structure interaction and contact. And regarding the fluid structure interaction, you have 2 approaches. One is the so-called moving mesh method. You can imagine you have volume mesh, you have a simulation mesh, which is moving according to the movement of the leaflets. So if the leaflets are moving, you have a computational mesh, which is also moving together with the leaflets. Here, the challenge would be that you have an algorithm which moves the mesh and also keeps the quality of the mesh. Then the second approach is the so-called fixed mesh method. So imagine you have a fixed background mesh. This would be the fluid. And then you have an embedded function which follows the movement of the solid, of the leaflets. This is much more easier in a sense of you can keep the quality. However, because you approximate the movement of the solid, you cannot capture that exactly the movement of the solid. So both sides have their challenges and also their advantages, but also disadvantages. This is the first problem. And the second problem is you need to model contact. So we have the fluid structure interaction, and at some point, in order to prevent backflow, the leaflets are in contact. And for this, you need to model a function which detects contact in a sense of, okay, they are coming closer, the leaflets, and at some point you say, now contact is happening. So you have to detect contact. And once contact is detected, you also need to enforce the contact. So how do you model the contact itself? So these are 2 complex problems you need to model in order to be able to simulate the movement of the aortic valves. And so what we succeeded in our research was that we could combine all these complexities in one framework. So that means we could establish a mathematical and numerical framework to solve all these issues in one mathematical formulation, which we called unified continuum. So it basically means you model the fluid, the structure, and the contact with one continuum. And the trick was to include a phase function. This is either a phase function. Basically, it's an element of the mesh is either fluid or solid, and you can switch. So if you have contact, then a fluid element could be solid. And if the contact is released, this solid element goes back to fluid. So this was the trick to model everything in one. And so that this, we could, in that sense, we could build one framework to solve all this problem. And this was our, how to say, contribution to the research field of modeling the aortic valves. And yeah, I don't want to go more into details. I think it's best if the link is included in the in this video.
Yeah, absolutely. And it sounds like you've made some pretty wonderful advancements, and when it comes to modeling. And how do you see that when it comes to the future of these applications in the medical field? Or what can CFD do, for example, for the future of medicine?
Mm-hmm. It's a good question. Yeah, but it's very important, I think, because what is the contribution for our work? What is the contribution for our research for society, I think? And it always accompanied myself when I did my research. So according to the World Health Organization, cardiac disease is the #1 cause for death. So therefore, understanding the normal function, but also dysfunction of the heart is vital. And nowadays, with the advancement of algorithm, but especially with the computational power, CFD is emerging as an important tool to enhance our understanding of the function of the heart. And in that sense, offer the possibility to be included in decision-making when it comes to treatment or diagnostics. For example, the treatment can be made patient-specific. You can run large-scale studies. And this is much more easier with CFD because you can much more easily tune different parameters. And this makes CFD as a candidate to support, complement, and also explain the functions which can be observed in a clinical setup in more details. And maybe there are also details or information which might not be accessible in a in vivo measurement. So it definitely can support and complement the traditional way of treatment. And for me, when I was working with the heart in my research, I think the key point, or like one of the key elements in order to make CFD one of an important tool in a medical setup, it's that all these different fields come together. When working with the heart, this is very interdisciplinary. You have engineering, you have mechanics, you have mathematics, you have numerics, you have visualization, this kind of the engineering part, but also you have all these experts in the medical field. And I think the key that we can use CFD in the future in a clinical setup, all these fields need to come together and speak or find a common language. In a sense of common language is in a sense of to find a common goal, and also to find what can we do now, what can we do maybe in a year, or what is our vision in the future. And sometimes it's not that easy because we have different backgrounds, we have different interests. But if we can find such a common ground, and CFD, I think CFD can be very powerful in the future.
Right. Well, I want to thank you for your research and your contributions to both the medical field and to Ingrid Cloud. And to our viewers, we'll leave a link to Jeannette's publication in our post below. Thank you.
Thank you. Okay.